In this video, we're going to go over some practice problems from Chapter 10 and Chapter 5 from our textbook. Starting with Chapter 10 here, we're looking at hypothesis tests regarding a parameter. And for Section 10.1, we're looking at the language of hypothesis testing. So for question 14 here, for this scenario, we're going to state the null and alternative hypothesis in words. And then for part B, state these guys symbolically. And then for part C and D, we're going to explain what it would mean to make a type 1 and a type 2 error, respectively. So for this scenario, we're told that historically the time to order and deliver a pizza at Jimbo's Pizza was 48 minutes. So the owner, Jim, implements a new system for ordering and delivering pizzas that he believes will reduce the time required to get a pizza to his customers. So with this information, we can easily identify what the null and alternative hypotheses are. So the null hypothesis is going to be the mean time to deliver a pizza at Jumbo's Pizza is 48 minutes. That's what we know to be true historically. And then with this new system, we believe that the time required to get the pizza is going to be less than 48 minutes. So that'll be the alternative hypothesis. So I'm going to go ahead and write that in words. Okay, so we have our hypotheses stated in words for part A, and then for part B, we're going to do so symbolically. So we know the null hypothesis, which we're going to call H naught here, is that the mean time to deliver a pizza is 48 minutes. So we're going to have mu here representing our mean is equal to 48 minutes. And then for our alternative hypothesis, we're going to have that this mean time is less than 48 minutes. So that's what our hypotheses would look like symbolically. And then something to note here is that we have a left-tailed test in this case, since this mean time is going to be less than 48 minutes. Now, for parts C and D, we want to explain what it would mean to make a type 1 and type 2 error. So remember, a type 1 error would occur when we reject the null hypothesis when the null hypothesis is actually true. And then a type 2 error would be that we do not reject the null hypothesis when the alternative hypothesis is true. So with this information, we can write these guys down here. So for a type 1 error, it would mean concluding that the new ordering system reduces the time required to get a pizza to below the 48 minutes when actually the new ordering system does not reduce this time. And then making a type 2 error would be concluding that this new ordering system does not reduce the time required to get a pizza to below the 48 minutes when actually it does. Okay, so I'm going to write that down for us. Okay, so I have that written down for us for part C and D. So remember for part C, we are explaining what it would mean to make a type 1 error. So remember for a type 1 error, we're rejecting the null hypothesis here. So we're going to conclude the alternative. We're concluding that the new system reduces the delivery time to less than 48 minutes, but this is not true in a case of a type 1 error. We reject the null hypothesis when the null hypothesis is in fact true. And on the other hand, for a type 2 error, in this case, we do not reject the null hypothesis. So we're going to conclude that the new system does not reduce the delivery time to less than 48 minutes, when in fact, for a type 2 error, the alternative hypothesis is true. All right, so let's look at this next question here. So for question 36, according to the CDC, 15.2% of American adults experience migraine headaches. And we know that stress is a major contributor to the frequency and intensity of these headaches. So a massage therapist feels that she has a technique that can reduce this frequency and intensity. So that's our scenario. And then for part A, we want to determine the null and alternative hypothesis that would be used to test the effectiveness of this therapist's techniques. So remember our null hypothesis, which we denote H naught here, is going to be the statement to be tested. So this is assumed true until we prove otherwise. So what we know to be true is that 15.2% of American adults experience migraine headaches. So this is the portion of the population. So in this case, we're going to use our variable P. And so our null hypothesis is that P is equal to 15.2%. So our alternative hypothesis then, H sub 1 here, is going to be that P is less than this 15.2%. That's what we're trying to test. We're trying to test the effectiveness of the massage therapist techniques, and she believes she can reduce this frequency and intensity. So less than 15.2%. So in this case, again, we have a left-tailed test. All right, for part B, a sample of 500 American adults who participated in this program results in data that indicate that the null hypothesis should be rejected. So we're going to provide a statement that supports the massage therapist program. So if the null hypothesis should be rejected, this means that there is sufficient evidence that the alternative hypothesis is true. So in this case, there's sufficient evidence to conclude that the therapist techniques does reduce the frequency and intensity of the headaches to below this 15.2%. Okay, so I'll go ahead and write that in here for part B. Okay, so I have that written in here for part B. In this case, we are rejecting the null hypothesis. So, keeping that in mind for part C, suppose that the percentage of patients in the program who experience migraine headaches is 15.3%. So, was a type 1 or type 2 error committed? So, in this case, this would be a type 1 error. What happened was we rejected this null hypothesis, so we concluded that the alternative was true. However, as we can see, the alternative hypothesis is not true. So, this is a type 1 error because the null hypothesis was rejected when in fact it is true. So I'll just go ahead and write, this would be a type 1 error. All right, so this brings us to section 10.2, where we're looking at hypothesis tests for a population proportion. So for question 12 here, given this information, we want to test the hypothesis using the classical approach and the p-value approach, and then we also want to verify the requirements of the test. So we're just given this information here. We have our null and our alternative hypothesis. We have our population and our sample size, and then we also have our level of significance. So in this case, we are going to assume that the null hypothesis is true until proven otherwise. So our p naught value is going to be the null hypothesis, this zero point 0.4. It's also reasonable to assume that this data is from a random sample and that the sample values are independent of each other, but we do also want to show that this quantity is less than, or sorry, is greater than 10. So we're just going to plug in our known information here. This is going to give us, we know n is 1,000 times zero point 0.4 times 1 minus zero point 0.4. All right, so this quantity is going to be 240, which we know is greater than 10. So that's good. Next, what we want to do is find our sample proportion and our test statistic. So the sample proportion, which we denote as p hat here, is going to be our x. So this 420 over our n value. So this is going to be 0.42. And then we'll use that information to find our test statistic. So our statistic is this z naught value, and it's given by this formula. This whole thing is under the square root. Okay, so this is our test statistic, and so we're just going to plug in our known values. We found our sample proportion to be 0.42, and we know our p naught is zero point 0.4. So that's all we're going to have in the numerator. And then in the denominator, we're going to plug in this 0.4, 1 minus zero point 0.4, divide this by our n value, and then take the square root of this whole thing. All right, doing so, we're going to get this. This is approximately 1.29. Okay, so with this information, we can start answering parts A and B of this problem here. So for part A, we're going to test the hypothesis using the classical approach. And because this is a two-tailed test, we can determine the critical values at our given significance level. So we're going to have just plugging in our alpha value, and then we're also going to have the positive version of this. All right, and then we can refer to this table from our appendix here. So if our level of significance is 0.01 and we're looking at a two-tailed test, then we're going to get plus or minus 2.575. So this is going to be negative 2.575, and this one's going to be positive. So what's happening here, since we have a two-tailed test, let's draw a diagram here, just so we can see visually what's going on. We have our curve, and then we know that our test statistic was 1.29, so that's going to be somewhere around here. And then we're looking at our critical value to be negative 2.575. So that'll be somewhere around here. And then our positive version may be somewhere around here. So the area under the curve here and here, I'll put this in blue, is going to be our critical region. Okay. Now, if the test statistic were to lie in either one of these critical regions, then we would reject the null hypothesis. And actually, I have this table posted here if we're looking at our classical approach. If our test statistic is less than the negative value of this, or greater than the positive critical value, then we would reject the null hypothesis. So pretty much just saying if this test statistic does lie in either one of these regions, then we would reject it. However, we know our test statistic is not inside of these regions here. So we, in this case, will not reject the null hypothesis. So I'll write a little blurb for that here. So we have our conclusion here for part A, and then for part B, we are going to test the hypothesis using our p-value approach. So in this case, we're just looking at our test statistic. So again, let's draw a little diagram just so we can see what's going on here. So we're just looking at our test statistic. We're looking, in this case, since it's a two-tailed test, we're looking at the negative absolute value, which is in this case going to be negative 1.29. Let's say that's somewhere right around here. And then we're looking at the positive absolute value of this guy, which is going to give us 1.29. So the area under our curve in this region is going to be our p-value. So scrolling down to this table that I've pasted in, again from our textbook, we kind of have each scenario here. We're looking at two-tailed, left-tailed, and right-tailed cases for our p-value approach. So as I said, the sum of the area in the tails is our p-value. So in this case, with a two-tailed approach, we're going to be looking at 2 times this probability here. So we're looking at 2 times this probability that our random variable is going to be greater than the absolute value of our test statistic. So that's what we're going to find here. We're going to find our p-value. So in this case, our p-value is going to be 2 times the probability of this here, since our test statistic is 1.29. So just to emphasize what's going on here, we're looking for this p-value, which is going to be twice this quantity, because just this quantity here, this probability is going to be the area under the curve to the right of our test statistic. And if we multiply that by 2, we're going to get exactly the area under the curve to the left of this guy. However, we know from previous videos that if we want to find this area, we're going to use our standard normal distribution table, but that table gives us the area under the curve to the left of our z-score. So if we want to find the area to the right of this guy, we're going to have to take this whole thing and then subtract out what we find to the left of this guy. So this value is going to end up being 2 times 1 minus the probability that this guy is less than this 1.29. All right, so just to emphasize, we've seen this before in previous videos. This entire thing is the same thing as 1 minus this guy. All right, so what we're going to do then is go back to our standard normal distribution table here. So we're looking at 1.29. So 1.2 is there, and then 0.09. So that's going to give us a value of 0.9015. So we're going to plug this back into this formula here. So 1 minus 0.9015. This is going to give us 2 times 0.0985, which is the same thing as 0.1970. All right, so this is our p-value, and using this approach here to test this hypothesis, we can conclude that we do not reject the null hypothesis because the p-value is greater than our level of significance here. So if the p-value were less than alpha, we would reject the null hypothesis. So we'll say, since our p-value is greater than our level of significance, Do not reject the null hypothesis. All right, so if our p-value were greater than, or sorry, less than, we would reject the null hypothesis. All right, so that is how we would do our hypothesis testing using the classical approach and the p-value approach. In this next problem, we're going to be doing something very similar. We're told that in an American Animal Hospital survey, 37% of respondents stated that they talked to their pets on the telephone, and a vet found this hard to believe, so he randomly selected 150 pet owners and discovered that 54 of them spoke to their pet on the phone. So, does the vet have the right to be skeptical? And we're going to use a, 0.05 level of significance. So we're going to do something very similar in this situation. The first thing that we're going to do is write down our hypotheses. So our null hypothesis, remember, is going to be the statement that we know is true until proven otherwise. And that's going to be that the proportion of our population that talks to their dogs on the phone is going to be 37%. So we could also write this as a decimal 0.73. And the alternative hypothesis, H1 here, is going to be that this is not true. All right. Now, for this problem, it is reasonable to assume that the pet owners in the sample are independent, and it is given that this is that the sample is random. The next thing that we need to check is this quantity here and make sure that this is in fact greater than 10. Now, in this case, we're assuming our null hypothesis to be true. So this means P naught is going to be this 0.37. We also have our sample to be 150. So we're going to plug these values in here. We're going to have 150 times this guy times 1 minus this here. This is going to give us 34.965, which is in fact greater than 10. So the normal model may be used for this test. Okay, so from here, we need to find our sample proportion and our test statistic. So our sample proportion, which is going to be given by this p hat here, is going to be the 54 people who said they spoke to their pet on the phone over our sample of 150. So this is going to give us 0.36. And with this, we can find our test statistic. So that's going to be Z naught. We're just going to plug in our known information into the formula that we used last time, this guy here. All right, so this is going to give us, we're going to have 0.36 minus 0.37 in our numerator. In our denominator, we're going to have this here, and then we're taking the square root of this guy in our denominator. So doing so, this is going to give us approximately negative 0.25. Okay, so from here, we could use either approach since it's not specified in this question, but we're just going to do both for the purpose of this problem. So first, for our classical approach, we need to find our critical values. And since this is a two-tailed test, we know this from our hypotheses here, we are going to have two. We know that we're going to have negative z of alpha over 2 and positive z of alpha over 2 here. So just plugging in our known values, we have a level of significance of 0.05. So we're going to divide that by 2. This is going to give us z 0.025 here. And similarly for this one. Now going back to this table here, that's going to give us plus or minus 1.96. So we're going to have negative 1.96 and positive 1.96. Now notice our test statistic, this negative 0.25, lies in between these two values. So this automatically tells us that we're not going to reject the null hypothesis. So since our test statistic lies between these two values, we're not going to reject the null hypothesis. We also want to use our p-value approach, however. So what we're going to do is we'll write that underneath this. So for our p-value approach, we know that we're going to need to take 2 times the probability that this guy is going to be greater than our test statistic value. So greater than the absolute value of our test statistic, which was negative 0.25. Okay. Now, since we're looking at the absolute value, this is going to be the same thing as this here. All right, and just like we saw in the last example, we know that this is going to be rewritten since we're trying to find the area under the curve to the right of this guy as 1 minus this. All right, and then going back to our table here, we're looking at the value for 0.25. So this is going to give us 0.5987. So let's move this down. We're going to plug that in here. We're going to have 2 times 1 minus that 0.5987, which is going to give us 2 times 0.4013, which gives us this guy. All right, so we already know from our classical approach that our test statistic is in between these two values, so it's not in our critical region. And we just saw that the p-value is going to be greater than our level of significance. So both of those tell us that we're not going to reject the null hypothesis. So since we have this and our p-value is greater than our level of significance, do not reject the null hypothesis. All right, so this means there's not going to be sufficient evidence to conclude that the proportion of these pet owners that talk to their pets on the phone is different from the 37%. This brings us to section 10.3, where we're looking at hypothesis tests for a population mean. So for this first question here, to test mu is equal to 4.5, so the mean is equal to 4.5 versus the mean being greater than 4.5, a simple random sample of size 13 is obtained from a population that is known to be normally distributed. So with this information, if we have that our sample mean is 4.9 and our sample standard deviation is 1.3, we want to compute the test statistic. So we know that the test statistic, denoted as T naught, is given by this formula here. So what we can do is plug in our known values. And in this case, since we're assuming the null hypothesis to be true, this mu naught is going to be 4.5. So plugging in our known information, we're going to have 4.9 minus 4.5 in our numerator. In our denominator, we're going to have our standard deviation divided by the square root of our sample size. So plugging this into a calculator, this is going to be roughly equal to 1.109. All right, so that's the test statistic. For part B, we want to draw a t-distribution with the area that represents the p-value that is shaded. So we're going to draw our curve like that. Let's make it a little bit nicer. Like that here. Let's say our test statistic is somewhere around here, 1.109. Now notice, going back up to our hypotheses here, we're looking at a right-tailed test since we have this greater than sign. So the area that represents our p-value is going to be everything to the right of this 1.109. All right, now for part C, we want to approximate and interpret this p-value. In order to do so, we're going to be using this table here from our appendix. So the first thing we need to do is figure out the degrees of freedom in this case. And we know it's going to be n minus 1, so we're going to have 12 degrees of freedom. So with this, we're going to find in this first column where we see R12. Now going back up here, remember our test statistic is 1.109. So in this row corresponding to 12 degrees of freedom, we want to find the values closest to 1.109. So notice this first value here, this 1.083 is pretty close, and then the next one over is 1.356. So clearly our test statistic is going to lie in between these two values. So this means our p-value is going to lie in between this value and this value here. So we're looking at the area in our right tail. So our p-value is going to be in between 0.10 and 0.15. All right, so with this information, let's answer part D here. If the researcher decides to test this hypothesis at the zero point 0.1 level of significance, will the researcher reject the null hypothesis and why? So remember, if our p-value is less than our level of significance, we reject the null hypothesis. And in this case, we just figured out that the p-value is going to be in between 0.10 and 0.15, and our level of significance is 0.10. We know the p-value is greater than that, so in this case, we're not going to reject the null. So no, do not reject the null hypothesis, since our p-value is greater than our level of significance. All right, so let's look at this next question here. So the ACT is a college entrance exam. ACT has determined that a score of 22 on the math portion of this exam suggests that a student is ready for college level mathematics. So to achieve this goal, the ACT recommends that students take a core curriculum of math classes given by these guys here. So suppose a random sample of 200 students who completed this core set of courses results in a mean ACT math score of 22.6 with a standard deviation of 3.9. So do these results suggest that students who complete the core curriculum are ready for college level mathematics? That is, are they scoring above this 22 on the math portion of the ACT? Okay, so first we want to state the appropriate null and alternative hypothesis. So the null hypothesis is what we know to be true currently. So that's going to be denoted by H naught here. And that's that the mean is going to be equal to that score of 22. And then the alternative hypothesis is what we're trying to test. Are they scoring above a 22 on the math portion of the ACT? So our mean is going to be greater than this 22 here, right? So in this case, we're looking at a right-tailed test. For part B of this question, verify that the requirements to perform the test using the t-distribution are satisfied. So let's just do bullet points for this one. We know that the sample size is random. We were given that in the problem statement here. So we'll just state that sample size is random. We also have this, the sample size is 200, which is greater than, or at least 30. And then it's also reasonable to assume that the sampled values are independent. So I'll just state that. Reasonable to assume the sampled values are independent. All right, so that brings us to part C here. So we're told to use the classical or p-value approach to test the hypothesis in part A with the 0.05 level of significance. For this problem, I'm going to be doing both methods, so you can check your work for whatever method you choose to use. So the first thing that we need to do is find our test statistic. Since we're using our t-distribution, this is going to be given by t naught, but it's going to be the same formula. We know that it's going to be our sample mean, which was given in the problem as 22.6. And then we're going to subtract out our mean that we're assuming to be true in this case, which is 22. This is going to be in our numerator, and then in our denominator, we're going to have our sample standard deviation, which is 3.9, divided by the square root of our sample size. So this is going to give us approximately 2.176. So this is our test statistic. And this statistic follows a t-distribution with degrees of freedom being 199. And so with this classical approach, we want to find the critical value. And what we can do is we can go up to this table here, look at the area in our right tail for our t distribution. If we have the full table all the way at the end, we're going to look for degrees of freedom close to 199. But that table only includes values from or up to 100 and then jumping to 1,000. And then the last value in that column there is our z value. So for large sample sizes, like in this case, we have a sample size of 200, the t-distribution approaches the z-distribution. So in cases like this, we can use the z value for our calculations. So if we looked at this table, we would easily find that z value. It would be the last guy in this column here, and then we'd look at the corresponding area for a significance of 0.05. We can use that table. We can also use the tables that we saw here in this appendix. So for the level of significance of 0.05 in a right-tailed test, we're going to take the z-value of 1.645. So a couple different ways to get there, but we do get that our critical value for this level of significance is 1.645. Now, since our test statistic, the 2.176 is greater than our 1.645, our critical value, we're going to reject the null hypothesis. So since this is the case, we're going to reject. So this is our classical approach. And then for our p-value approach, let's do that over here. We need to find the p-value. So going back to this page here, we have all these tables. We're looking at a right-tailed test. So our p-value is going to be this probability here. So we want to find the area in under this curve. So I'm going to use that formula. Our p-value is going to be equal to this probability here. And then we know that if we're trying to find the area under the curve to the right, this is going to be the same thing as 1 minus this probability, just like we've seen in past examples here. All right, so this is going to be the same thing as we need to go back to our table here and find what this value is going to be. So going back to this table, we're looking at 2.176. So we're going to go to 2.1 in this column. Let's do a different color. And then we're going to go to 7 in this guy. So 2.17 is going to be roughly 0.9850. So going back to this guy, we're going to end up with approximately 0.015. Now notice 0.015 is less than our level of significance. We are going to reject the null hypothesis. All right, so that is how we would use either the classical or the p-value approach to test those hypotheses. All right, and then for part D, we want to write a conclusion based on the results that we just saw in part C. So in part C, we concluded in both approaches that we are going to reject the null hypothesis. Now, if you remember, the null hypothesis says that the mean for the math portion of the ACT is 22. So if we're rejecting this guy, that means we are concluding this, that the mean is actually greater than 22. So in other words, the results that we saw in part C suggest that there is sufficient evidence to conclude that students who complete this portion of the ACT are ready for the college level mathematics. So I'll write a blurb for that here and that you can check in the solutions. This brings us to section 10.4, where we're looking at which method to use for hypothesis testing. So we have this little diagram that I took from our book. So the first thing that we need to look at is what parameter is being addressed in the hypothesis. So if we're looking at the proportion, then we're going to use this normal distribution that we saw in section 10.2. If we're given the mean, then we're going to use our t-distribution here that we saw in the last section. And then if we're given the standard deviation, we'd use the chi-squared distribution, but we're not going to go over that in this class. But if you are curious, you can look at some practice problems from section 10.4. Okay, so with that, let's look at this example. So suppose the mean wait time for a telephone reservation agent at a large airline is 43 seconds. So a manager is concerned that business may be lost due to customers having to wait so long. So to address this concern, the manager develops a new airline reservation policy that is intended to reduce the amount of time an agent needs to spend with each customer. So we have a random sample of 250 customers with a sample mean of 42.3 seconds and a standard deviation of 4.2 seconds. So using this level of significance here, do we believe the new policies were effective, and do you think the results have any practical significance? So, the first thing that we need to do is we need to write down our hypotheses. And actually, before we do that, let's figure out what method we're going to be using in this case. Notice in our hypothesis in this problem statement, we're looking at the mean wait time. So this means we're going to be working with our t-distribution. Okay, so like I said, let's write down our hypotheses. Our null hypothesis given by H naught here is going to be that the mean wait time is the current wait time, which is 43 seconds. And then our alternative hypothesis, we want to figure out if this new policy that the manager develops is going to make the mean wait time less than 43 seconds. So we're looking at a left-tailed test in this case. Okay, now we also want to make sure that the requirements for this t-distribution are satisfied, just like we saw in the last example. We do know that this is going to be a random sample of 250 customers. We also know, like I said, the sample size is 250, so that's at least 30. So let's again do some bullets. So we have a random sample of 250 people, which is at least 30. And then we can also assume that the sample values are independent. So sample values are independent. Okay, so that's done. The next thing that we need to do is find our test statistic. So this is going to be given by T naught. We know that this is going to be our mean time here. So this is going to be 42.3 seconds minus our mean from our null hypothesis. That's going to be in our numerator. And our denominator is going to be our sample standard deviation divided by the square root of our sample size. So plugging this into our calculator, we're going to get that our test statistic is approximately negative 2.635. Now, this test statistic follows a t-distribution with our degrees of freedom is going to be 249. And in this case, I'm going to use the p-value approach. So we want to find the p-value. So going back up to, I know this is a lot of scrolling here, but going back up to this guy. So if we're looking at a left-tailed test, we need to find this probability here. So this one's a little bit easier. We don't have to take this whole thing and subtract out everything to the left because we're looking at the area to the left of this guy anyway. So we want to find this probability. So this is going to be And this is going to give us approximately 0.0043. So we just find this value by looking at the table for our standard normal distribution, and we're looking at the one where all of our z values are negative in this case. So we have negative 2.6 in that first column, and then we're going to go to the column that has 0.03. We're going to get approximately this value. Okay, so with that, notice our p-value is 0.0043. Now, this guy is going to be less than our level of significance that we were given in this problem, 0.05. So in this case, we're going to reject the null hypothesis. Okay, and then going back up to our problem, we have a couple questions to answer. So using this level of significance, do you believe the new policies were effective? So since we're rejecting the null hypothesis, we're saying that the mean time is no longer 43 seconds. There is sufficient evidence to conclude that the new policies were effective. So we'll say, yes, the new policies were effective. And then the next question that we want to answer is, do you think the results have any practical significance? In order to answer this, we're going to look at the difference in mean wait times. So the mean wait time in the sample was 42.3 seconds, and we were given that the mean wait time originally was 43 seconds. So the difference between these guys, so we'll look at the difference in mean wait time is just going to be 0.7 seconds. Now, this is a very small change in mean wait time. So in this case, there's not much practical significance for this particular situation. So we'll say, therefore, so there's not much practical significance since this difference is just 0.7 seconds. So customers are really just waiting 0.7 seconds less. So this brings us to section 5.1, where we're looking at probability rules. So for question 28 here, we're going to exclude leap years from the following calculations and assume each birthday is equally likely. So for part A, determine the probability that a randomly selected person has a birthday on the first day of a month, and we want to interpret this probability. So we know that there are 365 days in the year, and so we're going to assume that a birthday is equally likely to fall on any day of the year. So this means the sample space is going to contain those 365 days, and they are 365 equally likely outcomes. So our sample space, denoted this capital S here, is going to be the first, second, third, all the way up to the 365th day of the year. Now, 12 of these days are the first of a month, since we have 12 months in a year. So the probability that a randomly selected person has a birthday on the first of the month, so we'll say first of month here, is going to be those 12 options out of the 365 equally likely outcomes. So this is going to be approximately 0.0329. So interpreting this probability means that if a bunch of individuals are chosen at random, then close to 3.29% of them will have a birthday on the first of the month. So say, we'll say approximately 3.29% of people will have a birthday on the first day of a month. Okay, and then for part B, we're going to do something similar. We want to determine the probability that a randomly selected person has a birthday on November 8th and interpret this. So November 8th is only one option out of the 365 options that we have. So the probability that someone's born on November 8th is just going to be one, since we only have one of those, out of the 365 equally likely outcomes. And this is going to be approximately 0.0027. Okay, so this means that approximately 0.27% of people will be born on November 8th if we were to select a bunch of individuals at random. Now, for the next question, we're told that a survey was conducted by Wakefield Research in which participants were asked to disclose their favorite night to order takeout for dinner. And so the following data here is based on their results. So For part A, we want to construct a probability model for favorite night to order takeout. And now, as you can see, I already have that on the right-hand side here, just in the interest of time. But this is just a table that breaks down all of our possible outcomes, so all of these days of the week and their corresponding probabilities. So for part A, I'll just state here, we do have 40 outcomes in our sample space. That's given by the table in this problem. But we also have 7 equally likely outcomes, and those are the days of the week. Okay, so this is our probability model for part A. Now with that, for part B, what is the probability that a randomly selected individual would choose Friday as their favorite night to order takeout? So this is going to be the probability that Friday is their favorite night to order takeout. We're just going to go back to this probability model. We're going to find 0.35 here, or 35%. And then for part C, would it be unusual for an individual to state their favorite night to order takeout is Tuesday? So going back to this probability model, we're just going to look at all of the days of the week and their corresponding probabilities. Now notice that the lowest probability occurs on Monday and Thursday. Okay, so everything else is greater than these values. So any day stated as their favorite day of the week would not be unusual if they're greater than these lower values here. So we would say this is not unusual since the probability that someone says Tuesday is going to be 0.125, and this is greater than the lowest probability that we saw of 0.05. Now in section 5.2, we're looking at the addition and complement rules. So let's illustrate this with question 14. We want to find the probability that the event E and the event F is going to occur if we're given that the probability of E or F occurring is 0.6, the probability of E occurring is 0.25, and the probability of our event F occurring is 0.45. Now this here is the general addition rule. So we can easily find this just by plugging in the given values. But just so we can visualize what's happening here, we like to use Venn diagrams for these types of problems. So what we're going to do is we're going to have this first circle representing our event E, and this second one representing our event F. And these guys are going to be enclosed in a rectangle, which is going to be our sample space, which I'll call S. So we want to find the probability that E and F are going to occur. Let's say we want to take all of this. We want to take the probability that E is going to occur, and we want to take the probability that F is going to occur. Notice when we do that, we took this intersection of these guys twice. We took it when we took this entire thing, and we also took it when we took this whole thing here. So in order to find the probability that E and F are going to occur, we have to subtract out this extra portion that we counted twice. So that's where this formula comes from. We're just going to plug in the given probabilities. We're going to have 0.25 plus 0.45, and then we're going to subtract out that zero point 0.6 here. This is going to give us 0.1. Now for this next example, we're going to do something similar, but we're looking at two different rules. So, in the game of roulette, a wheel consists of 38 slots, numbered 0, 0, 0, 1, 2, all the way up to 36. The odd number slots are red, so I have this event here in red. The even numbers are black, I got this guy here, and the numbers 0 and 0, 0 are green for this event. To play the game, a metal ball is spun around the wheel and it's allowed to fall into one of the numbered slots. So for part A, what is the probability that the metal ball lands on green or red? So I have this formula here. This is the addition rule for disjoint events. So these guys are mutually exclusive. They don't have any outcomes in common. So no intersection like we saw in the last example. And this is displayed here with these three events not intersecting. So if we want to find the probability that green or red is going to occur, we're going to find the probability that green occurs plus the probability that red occurs. So we know that out of the 38 slots, so we have 38 events here, two of them are going to be green. So the probability that the metal ball lands on a green is just going to be 2 out of the 38 slots. Now, the probability that a ball is going to land on red here is going to be 18. We have 18 outcomes out of the 38. So this is going to be 20 out of 38, which is approximately 0.526. So that's the probability that the metal ball lands on green or red. Now, for part B, what is the probability that the metal ball does not land on green? So this is going to be our complement rule. Now, let's do another Venn diagram here. Let's say the probability that the metal ball lands on green is represented by E here. And remember, this is going to be in our sample space in this box here. And what we're going to call on the outside of this box is our sample space, or everything that is not E, which we denote as E with a little C up here. This is the complement of E. So everything that is not going to happen in this event here. And we know that the total probability is always going to be 1. So if we want to find the probability that the metal ball does not land on green, so everything here on the outside of this circle, we're just going to take the entire thing minus the probability of everything here. So we know that the probability that the metal ball lands on green is 2 out of the 38 slots. So the probability that it doesn't land on green is going to be 1 minus 2 out of 38, which gives us 36 out of 38 if we get a common denominator, which is approximately 0.947. So that would be the probability that the metal ball does not land on green. So this brings us to our last section in this video where we're looking at independence and the multiplication rule. So for question 16 here, Christmas lights are often designed with a series circuit. So this means that when one light burns out, the entire string of lights goes black. So suppose that the lights are designed so that the probability of a bulb lasting 2 years is 0.995. And we're told that the success or failure of a bulb is independent of the success or failure of other bulbs. So although when one light burns out, the rest of the string lights goes black, that doesn't mean that the rest of these lights actually failed. It doesn't mean that they actually burned out. This just happens due to this design here. So we are dealing with independent events. Now, for part A, what is the probability that in a string of 100 lights, all 100 will last 2 years? So we have the multiplication rule for independent events here. If we want to find the probability that event E and F occurs, this is going to be the probability of event E times the probability of event F. So for this problem, we want to find the probability that all 100 bulbs last 2 years. This is going to be the same as the probability that the first bulb lasts and the second all the way up to the 100th bulb lasting. So this is going to be the probability that the first bulb lasts times the probability that the second, all the way up to the probability that the 100th bulb lasts. So we know that the probability of a bulb lasting 2 years is given by 0.995. So this is going to be 0.995 times 0.995 times 0.995 100 times. So we can write this in shorthand. This is going to be 0.995 raised to the 100th power because we're multiplying 0.995 times itself 100 times. So plugging this into our calculator, we're going to get approximately 0.6058. Okay, now for part B, what is the probability that at least one bulb will burn out in 2 years? So we want to find the probability, oh, that at least one bulb burns out in 2 years. Well, we just found in part A the probability that all 100 will last 2 years. So in this case, we can use our complement. The probability that at least one is going to burn out is going to be 1 minus the probability that all of them last. So we're using our complement rule that we saw in the last section. So the probability that 100 will last 2 years, this is going to be 1 minus 0.6058. So this gives us 0.3942. Now, for this last question here, question 20, suppose that a company selects two people who work independently inspecting 2x4 timbers. So their job is to identify low quality timbers, and suppose that the probability that an inspector does not identify this low quality timber is 0.20. So what is the probability that both inspectors do not identify a low quality timber? So the probability that both, I'm just gonna say fail, so they do not identify. So again, we're going to use our multiplication rule. So this is going to be the probability that the first inspector does not identify the low quality timber. So that's going to be 0.20 times the probability that the second guy also does not identify the low quality timber. This is going to give us 0.04, and so that will also be 4%. All right, now for part B, how many inspectors should be hired to keep the probability of not identifying a low quality timber below 1%? So, from part A, we know that if we just have two inspectors, clearly that's not going to be below 1%. So what we're going to do in this case is we're going to check three. So we're going to say the probability that three fail. This is going to be 0.20 times itself three times, which we know we can just write as 0.20 cubed. Now, plugging this into our calculator, we're going to get 0.008, which is clearly less than 1%. This is going to be 0.8%. So in order to make sure that the probability of not identifying a low quality timber is below 1%, we would need to hire three inspectors. So I'll say that here. Um, And then for part C, interpret the probability from part A. So going back to part A here, um, we know that the probability that both inspectors fail or they do not identify a low quality timber is 4%. So this means that we would expect both inspectors to fail to identify this low quality timber about four times out of 100. So I'll go ahead and write that blurb there, and that'll be in the solutions.